promised, we start with the construction. So we have what? We have principal bundles, right? And we have vector bundles. And so there's a way how to get from the right hand side to the left hand side, which is called frame bundles. And there's a way how you go from left to the right. And well, so if you go by this arrow, then you use what's called, or you end up with what's called associated vector bundle. The construction goes like this. So you need, well, fix your principal G bundle. So it's P over X, and the projection is pi. So this is principal G bundle. So your Lie group is G. And then also you need to fix, so this is like initial data. Also what you need to fix is representation of G, finite dimensional representation. Representation is a pair like this. So this is a representation of G. V is finite dimensional vector space, and rho is homomorphism from G to GLV. Right, here dimension of V is less than infinity. And let us actually denote this dimension somehow. Say N. All right, and then I define the following. So notation will be, so my principal bundle is P. I actually multiply it by V, but overall. So what does it mean? So it means that I consider direct product with some and glue some points. The equivalence relation, and the equivalence relation is the following. So a pair here, P1, V1, is equivalent to the another pair here, P2, V2. If and only if, well, we can write P1, V1 as P2 dot G inverse comma rho of G V2. Right, so this is really, so what is going on here? So I have action of G on V, which is left action, right? This is my action. And I have action of G on each fiber, which is right action. And so this gluing is by using the action, right action on V and left action on rho. It's like you consider tangent product of left and right modules. So here it's the same idea, if you're familiar with such construction. Okay, so you glue like this, and then well, this is for some G, okay, for some G from the group. Well, I claim, so far this is just a, well, topological space, right? So this is manifold, and then I consider its you know, factorization of it, so it has some factor topology. But then I need to see that this is really. So I want this to be a vector bundle over X. So that's my goal, right? So I'm taking P, which is principal bundle, and I'm making a vector bundle over X. All right. So I would like to introduce vector bundle structure. Right? Well, first of all, I need projection pi v. Let me call it pi v. So this is from this associated thing, which I cannot call vector bundle yet, but I'm going to. So this should be from here to X. And it just takes a class like this and map it to pi of P. Where pi is this guy, right? Well, this is well defined because if you take another v here, well, if you take it, well, it's just well defined. It's just, you know, simple check if it's not obvious. All right. Because this is just the only explanation why it's obvious is just because G acts on fibers, along fibers. That's it. And pi actually, you know, chooses a point at the bottom of the fiber. All right. So this is pi. This will be my projection, and I also need trivialization maps. So if I have trivialization neighborhoods for P. So if U is some trivializing neighborhood of P, meaning that I have a homeomorphism psi from pi inverse of U to U times G, well, which is, you know, which satisfies certain properties that we discussed last time. Then I would like to construct psi v. So, well, sorry, here I should be what? Of U, right? Like this. So I need to construct psi v. Well, this is from pi inverse v of U, where pi v is this guy. So this should be, well, homeomorphism to U cross V. So again, we are building a vector space, a vector bundle, and this will be a vector bundle over X with a fiber V. And so this will be my trivializing map. All right, and trivializing neighborhoods will be the same as for P itself. So I just define it like this. So I take psi v. This lives inside this guy, and so this is some class with representative given by a pair PV. So V is a vector from V, P is a point in P capital. So, and I take a whole class, and I need to map it somewhere. So by definition, I map it to the following thing. So I map it to here. So the first entry will be pi of P, and the second entry, should be here. First entry is this one, and second entry should be in V. So I already have this V here, right? But I'm not taking it here. I rather need the following. So I use psi, this map, and well, P lives inside pi inverse of U, right? So I take psi, consider its value at P, and then, so value brings me here, and then I can project to the second component and get an element of a group, right? So how do the projection to the second component, let me denote it like this, P2. So then it will be an element of a group that can act on V. And so I act by this guy on V. And this will be my pair. So anyways, I'm kind of forgetting, so P is in the fiber, right, at the top of a point pi of P. So I'm forgetting which exactly the point in the fiber, so I'm kind of, taking a point in X only. But then I'm going back to the point P, kind of this information where my P was, right? I'm extracting from this diffeomorphism, right? So kind of I'm going. Yeah, so I'm going back by G, but this is the same as, moving this point V by G. Anyways, so this is the construction. What we need to check really is that this is well defined. Maybe this also will be some justification of the construction. So this so psi V is well defined. So if I take some other representative of a class, say P dot G inverse, comma, GV. Well, just according to a definition, this should be what? Pi of P dot G inverse, and then P2 psi P dot G inverse applied to GV, right? Well, of course, this guy is the same as pi of P, right? Because again, if we act, we never go outside of fiber, right? And the projection is just the same. So this is again pi of P. This guy, well, this is just because we need to use equivariance of psi, which just actually says that this is actually P2 psi. So psi commutes with the action with the right action on the fiber. Psi intertwines the right action on the fiber and right action of a group on itself. So therefore I can rewrite it like this. G inverse dot GV. Well, but this is an action, so this will be just the same. Well, this cancels this, roughly speaking, right? Action means that this is the same as pi 2 psi of p, but and then I apply g to v and then g inverse, then dot. And this is just identity and g. And so I go back to the old, to the same definition as I have here with the initial representative. Okay, so what I'm checking is that psi v is well defined. So I have one formula for this representative, another formula for this representative. I need to check that they give the same result. And indeed, the result is just the same. All right, so this is well defined, and also I would like to see that it is, well, it is always kind of, you need to convince yourself that it is smooth, but it is, because like all the, so here is just projections, multiplications, all that stuff. So you cannot lose smoothness anywhere. But also what we need is that we have psi v inverse. That is actually different. So psi v inverse, also it's not hard to just write down the formula explicitly. So I have x v, right, this which is a pair in here. And I need to pair it, I need to map it back to here. Well, I'm just giving you the answer. So this will be class with a representative, which is written like this: psi inverse of x e g. So this is an element of p, which lives in here, comma v. Right, so I'm just saying that okay, you need to choose some element in here, right? And so I'm choosing it as follows, right? V stays the same, and the first element is just well, I take this pair x and identity in EG, map it back by psi, and this will be my first entry here. Well, pi inverse of u lives inside p. Right. And yes, so this guy should live inside here. So first component should live inside p. Right. So that's it. And then, well, this is just, I present the formula. Well, it's either you just see right away that it is inverse, or you just check. But you just can end up with such formula. Just what would be the the only natural construction how you can obtain the inverse of this map. That's it. Okay. So I think this explains as good as I can explain why this is vector bundle. Okay, so I gave you trivialization and showed that it is really at least an injection, right? All right. So we have now vector bundle with fiber V, and you see our construction is universal, right? So now you have, so suppose that you have, well, now I would like to give examples. So if you have P P well, this kind of gives you back. So you have, suppose that you started with the vector bundle E, right? Then we know that we have GLR principal bundle, which we call like this, which is frame bundle. But then you can choose different. You can choose. You can now take this frame bundle as P in our construction, and choose different representations of GLR. So this will actually can give you. I don't know if we denote. Yes, okay, we denote like some like this, right? So if rho. So now let me write it like this. If rho is just an identity, right? So this is just from GLR to GLR, just tautological representation of GLR. Then you recover back E, actually, in your construction. Then P GLE times, well, V is in this case is just R, well, RR overall. So this is just E itself. But you can take, so this is how you can go back to E. But of course you can also, so this is more universal than this. Because now you can take different representations and construct symmetric power of E, well, exterior power of E, or actually any symmetrization of E that you want, really. Because, well, all these guys, well, S, K, Cn, lambda K, Cn, well, Cn, I don't know, just tensor product, K-fold tensor product, all this. So take V to be this guys. Then what we get is PGLE of times V over rho will be, well, symmetric tensor of E, exterior power E, or, well, E tensor K also. So all that sits inside this thing. So this thing is more universal than vector bundle that we started. We actually can take, if you know a little bit representation theory of GLN, you also can take what's called, well, you can, inside this guy, there are representations which are labeled by partitions of K, or Young diagrams with K boxes, right? So you just need, symmetrize or anti-symmetrize somehow this stuff, which is also called the representation of highest weight lambda. So you have like also more in more general, you have S lambda inside Cn tensor K, and in this way you can define what is S lambda E. So you have like more general construction for each partition of K. And this very is plays along with representation theory of GOP. That's what I want to say. All right.
Можно какой-нибудь пример вот, представления, которое нам задаст вот, симметрическую степень?
Ну, так вот, это представление. Ну, просто как действует группа на тензорной степени? Как действует группа вот здесь? Ну, она просто действует очень тупо. Я беру какой-нибудь, значит, V1, там, V2 и так далее. ВК. G на него действует, ну, просто как бы на каждый. Вот так. Правильно? Ну, может проверить, что это действие. Вот. Ну и видно, что формула симметричная относительно перестановок. Вот, поэтому вот это подпространство здесь, оно инвариантно относительно этого действия. То есть действием G вы отсюда никак не вылезете в другие подпространства вот этого. Ну, поэтому это подпредставление GLN. Вот. То есть вот вам прям V, а вот ρ. Вот конкретное представление. Вот, но то, что вы получите, прямо получите симметрическое. Ну, просто у вас получится как бы вот такое пространство над каждой точкой. Вот что у вас как бы получается. Симметрическая степень Cn. Ну, в данном случае, что, n это на самом деле, ну, r должно быть. Я как-то перескочил на другое обозначение. Okay. All right. So, any other questions? So I'm done with associated vector functions. Do you have any questions? Please ask. Otherwise, let's continue. So next thing that I want to discuss is called principal connection. So principal connection is a particular example. Well, it's an Ehresmann connection with additional properties. Namely, again, I need to start with principal bundle over X. So let be a principal G bundle, and well, it's just I need a little bit more notation for a structure that we already have. Maybe we have this notation. So I have an action of G on P from the right? So this is the same as map from G times P to P. So this is corresponding right action. But then I can actually fix some point here, and this will give me, for each element G, this gives me map from P to P, right? And this is just a notation. So if G is from G, then I will just write alpha G for a map from P to P, which is defined as follows. It's just alpha G of P is just one of the arguments just goes to the index. That's it. And this is also, remember, the same as just writing P dot G, so Gx on P from the right. And then by definition, connection, well, AHP. So this is horizontal, like a choice of horizontal bundle on P. So P is in particular fiber bundle, right? So I'm talking about Ehresmann connection here. On P as a fiber bundle. on P is called principal if it satisfies the following. I consider the fiber of this horizontal subbundle at the point P, but shifted by the right action by an element of G. And this is the same as taking the fiber at point P and then applying d alpha G. Well, at point P, of course. We already had a version of such thing when we said which principal bundles really give us just usual affine linear. Which Ehresmann connections gives us linear connections. So we have kind of the same thing where the action was by the group C, R star, right? It was just cascading. So here is just a generalization of what we have. Okay, so I'm saying if I have if I have a principal G bundle. So okay, this is the end of the definition. So next thing that I want to claim is that actually, if I have a principal bundle, then vertical subbundle is trivial. How to see that? Well, to see that, let me consider an element xi. So, sorry. An element xi. So this is inside G, which is a Lie group, Lie algebra of the Lie group G, which remember it belongs to. So this is an element of the tangent space at identity of G. So let psi be an element of a Lie algebra. Then I can consider a curve in G. So gamma psi of t. So this is curve in G such that any curve really, gamma psi of 0 is just identity. And well, the tangent space at 0 to this curve is my vector xi. So I'm saying that actually there is isomorphism of vector bundles P times G. So this is just a trivial vector. I'm looking at this as a trivial vector bundle over P with a fiber G to Vp. And it goes like this. So I just take P psi, very natural thing if you think about it, and so let me finish writing. So I take P, then gamma psi of t is just element of G. I connect by this element on a P from the right. That's what I'm doing. So this thing is a curve in P capital, right? So this is a curve in P capital, so I can consider its tangent vector at 0. And I'm saying that's what this is my place. Okay. Well, I don't know. Maybe it's good to write to draw a picture. So I have like x here. Well, actually p, right? So my base now is p. Well, okay, maybe it's better to write x because so x, right? And then I have fibers of p, right? Which are the same as I don't know. Well, it should be not drawn like this. Sorry. But it should start at some one point. So maybe like this, at the top of this point, right? Or maybe, okay, maybe just a line. Sorry. So this is a fiber and this is my G, right? So this is how my P looks like, and each fiber is G, and then well, G may be like curved, but on G, X, so G acts on itself from the right, and there is corresponding vector field, right? So if I have an action of a group, we discussed it last time when we talked about Lie groups, then there's homomorphism from Lie algebras to the vector fields on the Lie group, right? And so, of course, there's a vector field that looks along fibers, right? And this is exactly this vector. So I choose a point. So how do I make a vector out of it? I choose a point in P, and an element of Lie algebra, which is just direction. So this gives me a tangent vector along a fiber, and this tangent vector is just given by this formula. Right? I'm taking my action, which is action along fibers, and I consider like an infinitesimal shift by this action, and that's what's happened here. All right. Well, I'm saying that this is really an isomorphism of vector bundles over P. And so, therefore, VP is really trivial, isomorphic to this one. Okay, so my goal actually so I defined principal connection as a Ehresmann connection with some additional property. But my goal is to reformulate it. So there is another way how you can define principal connection. By actually giving some G-valued one form on P which satisfies certain property. So now my goal is to see what is this form. For this, okay, first I observe that I have such an isomorphism. Right, but also I have connection one form K, right? So consider connection one form K. So this is an element, this is a section of T star P tensor VP. Right? Well, it's a tangent vector and projects it to VP. So this is what. But I'm looking at it as a one form. Okay, using the philosophy from the last time. All right. So what I'm saying is that actually, if I use this identification, maybe let's call it star by star. Section of this bundle is the same as section of this bundle. Tensor tensor P times G. Like this. Well, I should say it's well, they are isomorphic, right, as vector space. I can identify them by just using this identification of vector bundles. All right, and so if I take, I just want some, so if I take K from here, I want some other letter to consider an image of K inside here, so this letter will be omega. And so this is, so notation for this guy will be omega 1 of P with values in G. So when I say one form with values in G, I'm in section of this vector bundle over P. Okay. So omega is small, is an element in here. Omega capital 1 G. Right. So this will be my G valued one form, but let me fix some defining properties for it. So first of all, if I have psi, I would like to define, so psi is an element of the algebra. So I would like to define psi bar. This will be an element of vector fields on P. And this just follows this picture. Nothing very like nothing non-trivial happens, right? So at each so I have like a very small action of G along fibers, which gives me tangent vector along fiber at each point. And so I'm just collecting all these tangent vectors, and this will be my psi bar. This will be a vector field on P. Okay. So namely in the formula, psi bar of P, right? So this is like vector field, and if I evaluate it at the point P, so this will be just definition by definition. I take P gamma psi prime at 0. Again, so the same formula and the same picture. I'm just, collecting all this data into a vector field that I denote psi bar. All right. Then just by construction, omega, it's a one form. If I evaluate it at psi bar, so psi bar I put inside. So psi bar I put inside this entry, right? I will have. I will have section of this trivial vector bundle. It means that just at each point of P, right, I will have an element of a Lie algebra, right, which will, right, and so this is just omega of psi bar. Well, I should evaluate it. So this thing is a function on P, with values in G, and so this is just psi for any P from P. So this is just, I don't know, this is, you know, rewriting in formulas really this picture again and again. But sometimes I will just don't try it. So I will abuse the notation and say omega of psi bar is psi, meaning this, that's for any P. Right? Because omega of psi bar is a function on P. Right? Function with values in the algebra. And so this is constant function, and each with the value psi. Okay? In short. So this is one property that I want to fix of omega. So if I have such a vector field, then omega of psi bar is psi. Another one, which is not, for which we should work a little bit, is concerns what's called adjoint action of a group on a Lie algebra. So, well, I have this map, which, so if I have some element G of my group, then I have map CG. So this is a map from G to G. Such that, well, I take H and conjugate it by G. So it's just conjugation. It's a smooth map because G is Lie group, and inversion and multiplication is smooth. So I can consider differential of CG at point E, right? So this will be from TEG to TEG, which is just from Lie algebra to Lie algebra. This linear map from Lie algebra, to Lie algebra. Okay. Let me call this map at G. At stands for adjoint. So this is really an adjoint action. So you see, if I have an element G, for each element G, I have a linear transformation of Lie algebra. So Lie group acts on its Lie algebra. So we have a representation which is called adjoint representation of a group on Lie algebra. But this is more about notation, and so I have the following proposition, which says that, well, I also had my map alpha G, remember? Alpha G was from P to P. Right? It takes an element P and, well, maps it to the action of, to the point which I get from the action by G. So proposition says that this adjoint and this alpha G, they actually are related in this following way. So you have omega, which is your connection one form, this one. You can pull it back by alpha G, get another form. If you evaluate it, so at some vector field V of P, this is the same as taking omega of V. Right, omega of V will be, again, G-valued function on P, G Lie algebra valued function, and I can apply it at G to it. And so this is the equality. Okay, so pulling back by the action is the same as of my one form, of my connection one form, is the same as applying adjoint action of a group on a Lie algebra. And this happens like pointwise. Okay, so this is a statement. Let's prove it. So proof looks like this. Let me take V. It's a vector field on V, any vector field, and V then can be decomposed into horizontal component and vertical component, right? And let me say that okay, I have VP, right? So which is just I'm fixing a point and some arbitrary point in P, right? So now this becomes a value of this vector field at this point. And so, there's the same decomposition, but K of VP is actually this will be a tangent vector, right? This will be a tangent vector in the direction of a fiber, right? So this is really actually given by some element of Lie algebra. Xi bar P, or some Xi. I'm not saying that any vertical vector field is Xi bar. I'm fixing a point, and at the point I can find Xi such that the corresponding tangent vector coincides with the vertical component of V at this point. Okay, so I found this Xi, then I can write the following thing. Alpha G star omega P of VP is the same as, this is just definition of that. What does it mean? Definition of alpha G plus what does it mean to pull back form, right? And what is the value of a pullback at VP? So I need to shift the point at which I evaluate by alpha G and evaluate it at dP alpha G of VP. So this is really just the definition of pullback. Okay? If I have some F, right, star of omega P, VP, is just exactly omega of F of P, D, F of VP. It's just definition of pullback, nothing else. So this is it, but then dP alpha. So then I consider this decomposition of VP, and this gives me omega P dot G. Then I have dP alpha G of H of VP plus dP alpha G of Xi P bar. And then I need to do this. So now I'm using the fact that my connection is principal. because, well, this is really, so this guy belongs to HP of P, right? To the horizontal direction, right? And when I apply d alpha g, I end up in H P dot G, HP dot G of P. Of P. So this is because HP is principal connection. I'm using definition. So this one is horizontal, and omega, so it came from K, right? Because omega was a, so let me go back. Omega is really, if I'm thinking in these terms, is a projection to vertical bundle, right? So if I project something horizontal to vertical, it's just zero. So this component is just zero. So what's left is this guy. And this is like, this is why the whole non-triviality of this statement is that this vanishes and I can only work with this guy. Then what is left is omega p dot g of dp alpha g of psi bar p. But then this is really let me go here. But just by definition, this is omega p dot g of the tangent vector to the following curve. I applying alpha g to p dot gamma psi and then take prime of that at 0. It's just definition of what is psi bar and what is the differential of a map, really. All right, but then this equals to now I need to take to remember what was alpha j. So alpha j is really an action from the right. So this will be omega p dot g of p dot gamma psi g, well, dot g here, prime at 0. Right? But now let me use this trick. So let me plug in identity written as GG inverse here. Right? At the end, I'm going to. So my goal is to write this somehow as an adjoint action. Adjoint action came from the conjugation. So I will have to conjugate gamma by G. Right? So I need to plug in GG inverse here. Right? So this will be omega p dot g of, so here p dot g and here g inverse gamma psi g, and then of all of this prime at 0. But then this is the same as omega p dot g. Well, I am applying at g to psi. So this is another element of Lie algebra, right? And then I consider bar of it and this will be a vector field, at point P dot G. So you really need to consider what. So okay, so at G is from the conjugation, right? This point is because I'm applying this curve now, conjugated curve, to this point. And then bar is exactly the, well, because that's just how bar of an element of Lie algebra was defined, right? So that's what happened. Right. But then I have what? Yes. So this. So remember that I had I had omega of xi bar is xi, right? This expression. So omega of something bar is this thing. This is this thing. So I have at G of xi. Well, at the point P dot G. That's exactly that was exactly my condition, that omega of xi bar at some point P, right? I shouldn't write this, right? So this is just like that, right? So this is a constant function, right? For each point is just this element of the algebra. So what I'm writing, recall that we had this. Now I need to go, make it, so this is as simple as it gets. I just, so we are proving what? We are proving, we are proving this, right? So I need to go back somehow to omega of V, right? So I'm saying that, okay, let me go back, use the same exact thing. So it will be at G of omega P of xi bar at P. Again, I'm using this. Зависит от определения, конечно, да. Но мне, сейчас, а у нас какое-то, нужно, наверное, поправить, если там было неправильно. Потому что я хочу именно такое. Okay, let's go back and check. Yes, so I really wanted at G inverse here. Ну тогда это правое действие, но ничего страшного. Даже ну и хорошо, потому что альфа G это тоже правое действие. Вот. All right. So now, yes. So now we are here, and finally, well, I'm kind of going back to here, right? Omega P of xi bar P is the same as, so this is at G, right, of omega P. So I need this with, to replace this with V, and I can do this because xi, so xi P was K of VP, right? So this is H of VP plus K of VP. This component I can put back in because omega of H is 0, as we discussed. And K of VP is exactly psi bar of P. Again, because it's just psi was defined like that, right? And so therefore it is just add G of omega P of VP. That's exactly what we need. All right? So proposition is proved. Little bit.
Как мы, наверное, как мы убили, сейчас, вот слева, там, где, как мы убили этот компонентус H.
Да, и сначала я сказал, что вот это все равно лежит в горизонтальном. То есть действие G, у меня как, ну, значит, главная связность это выбор горизонтального, значит, горизонтального расслоения. Вот, такое, что он как бы действие G приводит к горизонтальному в горизонтальному. Ну, то есть действие G, вот я выбрал горизонтально, я подействовал, опустился там на уровень ниже, это все равно горизонтально осталось. Вот. И примерно это здесь написано, я все равно остался в горизонтальном. А омега это реально наша К предыдущая. Это значит, это проекция на вертикальную. Вот. Значит, если возьмем что-то горизонтальное, проектированное вертикальное, ну тогда получаем ноль. All right. So proposition is like a converse of this statement. So suppose that I have omega, which is one form from here, omega 1 of B with values in the algebra, such that, well, omega of xi bar is xi for any xi from G, and 2, well, this property also satisfies, meaning that alpha G star omega of, well, alpha G star omega of V is at G omega of V. So this is for any V from vector fields of P and for any G which is an element of Lie group. Then I can consider HP, a horizontal subbundle defined as the kernel of omega. Right, so we need to go back, and so this is gamma of T star P tensor P times G, right? So at each point P, I choose subspace of vectors such that plugging into omega, I get 0. Okay, so this gives me some subbundle of TP. All right, which is just kernel. Well, this is kernel of omega. So then this defines a principal connection on P. Proof? Well, we just need to check this property. I need to check what. So if I take V from my horizontal bundle, right? So so this is tangent So suppose that I take VP from T P such that it's in the kernel, right? So omega of P of VP is 0. Is it true that D alpha G of VP is also in the kernel, right? So I need to take omega P of this, and this is 0. So that's what we need to check, right? So my alpha moves horizontal to horizontal. Well, moves means that I'm applying action. Since I'm talking about tangent vectors, I need to take differential of an action, right? So I take something from the kernel, and I want to obtain something from the kernel. Let's check this. So this guy is the same. So omega P of dP alpha G dP alpha G of VP. This is the same as alpha G star. No, sorry. Should be. So this one is little bit not good because I need. So I take VP. It was a vector at point P. When I apply differential, it becomes a vector at point PG, right? So I need to apply alpha also to here, right? So P dot G. Anyways, I need to apply pullback with respect to G to omega. And then compute this at VP. This is just again definition of pullback. But this, now I'm using this property. So this is very helpful. So this will be at G of omega P of VP. But this is 0, right? Now this is 0. And that G is just linear map applied to 0, so this is just 0. And so this is very easy, this direction. Okay, so what is the conclusion? So conclusion. So therefore, we have the following equivalent definition of principal connection. Equivalent definition of principal connection. So definition. So principal connection is one form omega. So this is, well, Lie algebra valued one form. So it lives inside omega 1 of PG. Satisfying these two conditions. One and two, so let me not write it again. Okay, so this is exactly 11:20. let us have a break for 10 minutes and deal with characteristic classes. After the break.